Welcome back for another flight computer video. Today we're looking at the Aristo Aviat 617, which was the follow-up to the Aristo Aviat 616 that we took a look at in the last video. And these two flight computers are nearly the same. The big difference is the way in which they approach the wind solution, and we'll take a look at this in depth in just a bit. But before we do, many people say that the 616 is one of the best flight computers ever made, and in terms of functionality, it is all there. There's so many things you could do with this flight computer, but the construction is made of plastic, so it is relatively delicate. This card can snap and break, as we saw on the 616, and the paint can fade as well, as we saw on the 616, even though this device tends to be in pretty good shape. One of the ways it stays in good shape is it came in a nice slip cover. So for the 617, this is you just slide the device right on in here, whereas if you recall in the 616, it came in a nice zippered pouch. So we'll start this video by walking through a wind solution using the 617, and then we'll return to the front of the device to do a calculation on these rare outer scales. So let's start here. What's different about the 616? Well, it has this unusual wind bar to it, and the wind bar has some shapes on it, and those shapes correspond to a specific side of the card, and there's actually multiple cards that could be interchanged into this flight computer. So this card is the circle and square card, or the KD model. And so one of the problems that has always existed with flight computers is that as airplanes got faster and faster, you have to cover a larger range of speeds in these wind triangle calculations. And so Aristo's solution for this was to have different types of speed cards that could be interchanged into the flight computer. So when you're solving a wind problem, what you need to do is you need to use the symbol that's in the upper left-hand corner of the card with the wind bar as well. So let's make this concrete and just work out an actual problem here. So our true course is from the north. We're heading to the north, so we set that under our true index there, like so, 360. Then we set our wind, which is from the southwest, at 225. So then what we do is we take the 0, because that's the side of the card that we're on, and we set that to 225, or a wind from the southwest, which is also written there as well. And then what we need to do is we need to find our velocity of the wind, which is 50 kilometers per hour. Now, each one of these little lines here, radiating outwards, on the 0 scale, is 10 kilometers per hour. We'll use it as 10 units. So we're looking for this point right here, which is 50 kilometers per hour, which is our wind speed. And what we want to do is line that up on our true airspeed of 400 kilometers per hour. So again, we make sure we haven't moved anything. True index is north, wind speed is from the southwest, and I put the 5 on the 0 scale right there on 400, that arc of 400. And so now what I can read is my wind correction angle, so that dot would fall right on this line here for my wind correction angle of 5 degrees left, and under the grommet I would have my ground speed. So again, when I line this up just right, it's hard to read at this scale. It looks like 410, 20, 30, maybe about 433 or 434 would be our ground speed. So again, wind correction angle of 5 degrees to the left, and our ground speed 433 kilometers per hour. Now, just to show, again, I guess before we get there, it was not necessary to draw any dots, and maybe that was one of the things that was difficult about the E6B is you actually had to mark your wind dot, you had to remember where it was, whereas this wind bar makes that quite easy, and it's certainly less cluttered than the presentation that we saw on the 616. Now, on the 616 you didn't have to make a wind dot either, but you had to sort of find where you were and compare it against, again, all this other noise, whereas the 617 is quite simple. Now, let's do that same wind problem again, but we'll do it on the other side of the card, which is the side of the card that uses the square symbol on the wind bar. So the square symbol is over here. What we end up doing is putting the square on our wind speed, our wind direction, southwest. And the same thing, we find the 5 and we put that along our speed arc, that point, along our speed arc of 400. and we can read the same information. So we have our wind correction angle of 5 degrees left, and our ground speed is here in less resolution, but looks like it's between 430 and 440 kilometers per hour. So you can see how you can use the wind bar with different slides in order to find your ground speed or your true airspeed, depending on how you're working the problem. And so you can cover a wide range of airspeed. So this slide, on this side, goes from 100 units all the way up to 1,000 units. On the other side, it went from 150 to 750, which is why we got much better resolution with this side. Okay, and finishing up, I just wanted to look at one more interesting problem on the Aviat computers, which is the problem of finding the weight of fuel at sort of non-standard conditions. So most transport aircraft will order their fuel in weight and everything is taken care of. But in some cases, you may have to order it by volume. So a lot of times aviation gas is sold in gallons or in liters. And in order to convert that into weight, normally we just use a standard value. But it is possible for the fuel, you sometimes might notice this at the gas station, to be calibrated. The pumps are calibrated to dispense fuel at a given temperature and a number of other factors. So let's jump in and see how this works. So let's find how much 150 gallons of fuel weighs at a specific gravity of 0.72. Now that's going to be a standard value here. So what we do is we set under the US gallons flag here the quantity that we want to convert, which will be 150 gallons. So we set 150 to that flag like that. Then what we'll do is we'll go to the outside specific gravity in pound scale, and we set the value here to 0.72. And then what we can do is read the weight of the fuel inside that value, which ends up being 900 pounds. So this ends up being what we think of as a standard fuel conversion, where aviation gas weighs about 6 pounds per gallon. Okay, but what happens if it was particularly cold out, or it was a certain type of fuel mixture, and we found out from the people filling up the airplane that the specific gravity was actually 0.80. And specific gravity is it's a measurement that expresses a given density relative to the density of water. Anyways, we come back here, we would set the same value, so 150 US gallons, and we want to find the specific gravity at 0.80, and that is going to be 1,000 pounds. So we took on the exact same volume of fuel, but at this specific gravity, it actually weighs 100 pounds more, which could potentially put the airplane over gross weight. And likewise, if the specific gravity, maybe it was a super hot day, or again, the fueler just told the specific gravity today is 0.70, what we would do is we would use this outer scale again, set our specific gravity to 0.7, and read our value, our weight on the inside, which looks to me like 8.76. So we'll say 876 pounds. So that's what these scales are used for on the outside of the device. We have specific gravity for converting into pounds, and we also have specific gravity here for converting into kilograms. A very nice feature on this very full-featured flight computer. So that's it for today. That's it for the Aristo Aviat series, and thanks for watching.